Okay.
Looks like we're back up and running.
Right.
Okay, and which means that we're going to be back up and running with a demo.
Really? Again?
Yeah. Wow. That's what the slowpoke is for, right?
Yeah. I thought we were done with it already.
Well, I'm done. You're not.
All right. So you want me to run it again?
Yeah. Okay. So what are we doing now? It's like
just let it run.
Yeah, we're just letting it run. Okay.
Right. So we fixed the idle problem. We figured out that the huge idle time is actually the our driver not incurring too much of the load. So that's probably fine with our requirements if our use case was actually worded as we are bashing with the 1,500 users and we want to have this particular response time. This is probably fine. And now we are shifting to the other part of the performance tuning, which is Kirk is not familiar about. Yeah. When you're not when you're not only trying to meet the customer needs with the particular set of use cases, but you also want to get the resource consumption down. And it's really important in our cloud world when we actually pay for actual resources used there.
And that's what we do.
That's what we do.
And don't forget, if you're doing Android, you have to worry about
power,
battery.
Yep.
Right? Battery is a shared resource also.
I'm not concerned about Android at this point.
Right, I forgot. The Oracle guy's not going to mention Android.
What's that? What, again?
Yeah.
All right, so idle problem, we fixed that. What's our next step? We would actually go ahead and fix the concurrency stuff that we had already had fixed. So at that point, we would probably go for the application JVM level. We will see that there is lots of user time there. And when we have lots of user time but still not meeting our criteria, or we need to go deeper there, we need to follow through the 4 categories of issues that we might have there. First one, we have the JVM itself could burn the cycles. We could have the algorithmic problems in our application. We could have the memory problems in our application, which is more like hardware-centric view on the performance, or the CPU problems. It's appealing to see that most people are starting here. So when they see the performance problem, they just start the profiler and start to measure its performance while they didn't really check whether the application or JVM is actually busy. If application or JVM is not busy, it's useless to do the profiling because your problem is elsewhere. But we are now here. We had finished all this preparational work, fixed all this issue that led us to this user time there.
So my take actually on this previous slide, right, is that if we have lots of user time, right, we need some way of teasing out an algorithmic problems from the other CPU consumer, which is the garbage collection threads. And really the way to do that is to use some sort of garbage collection analysis. Typically, garbage collection logs is my main weapon in this case. And we'll look at the GC problem. And if the GC isn't running efficiently, then I'll move towards more of a memory-based investigation. And if the garbage collector is running efficiently, then we'll look more at an algorithmic strength reduction type of exercise.
Right.
Just to add to what the points that Aleksey brought forward.
I would try to go through the mind map as fast as possible because we want to get back to our demo there.
Yeah.
So let's go for the memory problems first. This is the very hardware-centric view. For the memory, everyone knows that CPU caches are small, so this is the obvious problems for the memory. Also, the problematic part is TLB. Who knows what TLB stands for?
You guys should.
All right. Are those your guys?
They
don't know what TLB is? You should fire them.
Yeah, they're gone.
Right. So the NUMA issues and the general memory bandwidth issues you might have there. Virtually all the applications that we have in our productions are getting memory dominators there, so the memory is major bottleneck there. Unless you do for the very high performance computing stuff, when you do lots of computation without actually accessing much of the memory.
So the TLB is translation look-aside?
Yeah, I will talk about this a little bit here. So TLB is the translation look-aside buffer. You know that our hardware operates in the virtual, our software operates in the virtual addresses, but our hardware operates in the physical addresses of the memory. So you need to have someone to translate those virtual addresses in your application address space to the physical addresses of the memory that you have. It's also complicated because the virtual address spaces of the processors could intersect and to do some sort of shared memory communication and stuff. So that should be fast enough because every single time you access the memory and you do that by virtual address, you have to convert that to the physical address, and that takes a lot of time for the operation system because it has all these page tables which actually have this mapping from the virtual addresses to the physical ones. So processors are getting smart about that and say, okay, we will have these caches which will translate that mapping from virtual to physical addresses. But that cache should be really fast, and so it is really small. You can't really increase that in hardware without incurring other penalties. So the way to go with that is to use larger memory pages. Luckily, our operation systems and hardware support large pages. So in Java, you can might as well use the use large pages there, and you will get rid of the TLB problems. It's almost easier to try to fix the TLB problem than actually diagnose that. But if you want to diagnose that, you have to go for the hardware counters to pick up your favorite tool for hardware counters. Like my favorite is Oracle Solaris Performance Studio Analyzer. Other guys are Intel XE amplifier.
Yeah, and in June we actually built our own that actually is pure Java on Linux that will actually program the performance counters on the chips. And one of the measures that we actually look for are TLB hit, miss, and walk lengths. And if those are out of tolerance, then that's certainly a use case or a condition where large pages are going to help you because it means that you're going to probably get a lot more cache hits in this particular case.
Yeah. Right.
And that can make a significant difference in performance.
Right. Okay, so
especially garbage collector performance.
Right. So caches. For the caches, we have two distinct problems. First one is capacity of the caches. Caches are small enough for the applications that we are dealing with. So what to do to fit in those caches? You have to exploit either temporal or spatial locality. How do you do that? You can actually read up any book on the cache architecture or even the Wikipedia article. It's very thoroughly explained there. We will just briefly walk over that. So for the temporal locality, you want to assess the data closer in time. So you want to assess the same block of memory frequently enough, then get over with it and start to assess another block of memory. So blocking decompositions, for instance, in algorithms can provide you that. For spatial locality, if this is something easier to be achieved, you can push toward a denser data set. In this sense, you can get more cached data when you see the ratio of cached and uncached data. So on 64-bit VMs, you can use compressed OOPS, which tries to have 32-bit pointers on the 64-bit JVMs, thus greatly decreasing the bandwidth and memory bandwidth and the data set.
Yeah, but there's no free lunch there.
Yeah, there's no free lunch because you have the conversion. Yeah. Right. Or you might as well go for denser data structures. I frequently have the question of how do we do the denser data structures in Java? And my usual retort to that is, if you ever use the linked list anywhere, that's bad. You should use array lists, unless you prove by some magic that the linked list is actually more applicable there. Because array list is much denser, and it works with the caches very, very efficiently, not unlike the linked list there.
Yeah, linked list has some bad garbage collection behaviors also, object nepotism, but we won't talk about that now.
So the coherence, When you communicate between threads in your application, you are communicating through the cache coherence, actually. You might think you are communicating through shared memory, but shared memory is actually the illusion. There is no shared memory at this point. There's just the illusion that hardware is trying to maintain at all costs. And most of the time, you are dealing with the cache coherency issues when you are having the transfers between the threads. So if you master the knowledge about cache coherence, you are actually mastering the knowledge about how to communicate between threads more efficiently.
Yeah. In this particular world, there's a number of operations that really make a huge difference. For instance, and anytime you pass through things like volatile and synchronize, that's forcing fences to be placed into your code.
Yeah, I will talk briefly about that.
Yeah.
Before I go for the pessimistic route there. So after you run out of caches, you meet with memory. You will meet the memory in one way or the other. And then your memory bandwidth starts to count. So that actually dominates your cache miss performance. So if you have the opportunity to make more faster memory, like go from the single channel to dual channel, or just get the faster memory sticks, that will greatly improve your performance because your cache misses would be faster.
But that's also dependent upon your bus speed and
yes.
everything that's also using your bus.
Yes, sure. So this is the bandwidth.
Right.
It's kind of strange to talk about the buses in 2013 because there's no buses on the most of the consumer hardware, even
right.
consumer hardware
right.
at
but
this
it's
point.
Still applicable.
Yeah, it's still the communication links there. Right. So we should have solved the concurrency problem in this step, but instead we did that, eliminate that synchronized lock from there, and that magically solved our concurrency problem. It didn't quite the same when you're dealing with the actual production code. The concurrency issues there are much more complex, and I want to give you a bit of the background on what's going on there. So in order to do that, I have this nice and cozy graph there, which tries to put the hierarchy between the communication primitives that we have in the language or the platform to communicate with. So we start with a plain unshared memory, meaning that we don't share any particular memory between the threads. It has the less power possible. You can't do anything with this memory. You can't actually use that to communicate with other thread. The harder primitive is the shared memory, which provides you with the means of the communication. So it's more powerful, but it's also more slower because you start to expose the communication patterns, you start to mess with the cache coherence issues, etc. Volatile is the more powerful primitive, which provides you, with addition to the communication, it provides you the visibility guarantees for this. So it's much more powerful than plain shared memory, but it costs you more. Atomics provide all of the above, plus atomicity of the change. Atomic sections, or you can sometimes call it spin loops there on the CAS spin loops, provides a group atomicity. Then you have the spin locks, which provide you another additional, very useful sometimes property, which is mutual exclusion. And then the weight locks as the most dominant and most powerful primitive of synchronization of all provides you blocking. So you can actually say, see that thread over there, you just go ahead and block it. So I have the power to block other threads. So why am I telling you this? Because this is the road to perfection. If you can choose the synchronization primitive that you are using for your communication, you have to choose the least powerful one that still meets the needs of your application, because that brings you more performance. So it's useless to say, if I need to just communicate one single value between the threads to wrap it up in the lock, you can just might as well mark it as volatile, because it's the least powerful primitive that brings you that effect without the incurred performance penalty of locks. Same goes with the atomics and whatnot. So this is the, you have to keep this picture in mind, and when you're selecting the primitive that you're using, select the less powerful one which still meets your application needs.
But you have to make sure that you pick the appropriately powered one.
Yes, right.
Because there's some effects that you can actually get, but like with volatile, that's related to, again, cache lines. So I don't know if you address this, but in this case, I'll defer the conversation to that. But just remember that, there's some strange effects that can happen because of the granularity of what we think of memory being partitioned up as to how it's physically partitioned up inside the core. In a core, we're partitioned as cache lines.
Right. All right. So other useful synchronization and coherence techniques are optimistic checks. So many primitives actually provide you with the way to optimistically check for some condition, in order to not to fall back to the pessimistic one, which presumably costs you more. So this is the example of the section which is one-shot fire action guarded by the atomic Boolean. So you can probably go ahead and just write the compare and set false true there, and have the try to do the compare and swap operation every time you meet this section. But CAS is more powerful primitive than just checking the doing the volatile read against that atomic Boolean. So I could actually do the optimistically check what is the value of this atomic Boolean before, in order to not to fall back to CAS if I know for sure that section has already fired.
So what's a CAS? So what is a CAS?
Compare and set. It's right there.
Compare and set. So how does that actually work then?
It depends on the hardware. Legacy hardware were actually locking up the memory bus for all other processors while they are doing the update, which acts like the common serialization point. Modern hardware is somewhat smarter. If you are caching against the cache line which you had already in your ownership or modified state there, you do not have to communicate that update with any other processor, because cache coherence does that for you already. So presumably the local caches are cheaper. By the way, the performance of the cache is actually the reason why we have the biased locking in JDK. Because the locking, which is with thin lock, which tries to acquire the monitor, is actually the cache against that monitor, and it costs a lot on the legacy hardware. So if you can spare that cache and use just the plain read, it actually beneficial.
Right. So a monitor is an operating system resource then, and you protect it with a value, and that value is like a lease or a thin lock. And so what you're going to do is to cache your thread ID into that memory location to say that I actually own this segment of code, right? That gets you mutual exclusion. And so when you're biasing when you're biasing a thread to a lock, and in essence what you're saying is that I don't have to do that CAS operation over and over again unless I get contention on the thread. At that point in time, what will happen
my
is
optimistic check will fail, and I will fall back to pessimistic.
Yeah, the CAS will fail, and when the CAS fails, then we're going to have to inflate that lock.
Right.
And we'll never be able to bias again.
So this is for optimistic checks. Another example is locking. When you have, for instance, this reentrant lock, instead of doing the lock, if you know that the critical section which is guarded by this lock is really small, it is probably convenient to try and lock it multiple times, waiting for this critical section to actually be freed. And so you will not have to block here, but you will spin a bit and then enter the critical section. It is not in the libraries. You will think, why, if this technique is actually beneficial, why it's not in the libraries there. And in fact, when you deal with synchronized, some sort of adaptive spinning is there. It's somewhat hard to do with the Java util concurrent cases, and not degrade general cases, because it's hard to distinguish the locks that are locking forever or locks that only briefly taken. So the common stance is that users that know they need that sort of spinning will do that by hand.
And so what you're trying to prevent here is an unneeded context switch, which could potentially be more expensive.
So this is voluntary context switch. This is blocking.
Right.
Which means that if my critical section is free in next microsecond, I will actually burn 100 microseconds just to get the context switch back.
Right. And so how big should count be?
Depends. Nobody really knows until you actually figure out for your particular application.
So can you say that hotspot in the spin lock case is actually, or adaptive spinning case actually profiles then?
Yeah, it actually tries to balance the number of successful spins and unsuccessful spins and try to balance that by changing that limit there.
And it would compare that against the cost of a context switch.
Yeah. All right. So another thing is striping. It is possible at times to split the shared state in the superposition of the local states so that you will not have the contention of the single memory location there. So if you go ahead for instance, thread safe counter there, it's a very silly idea to try and do the synchronized and increment the field there, because you will probably have the contention problem there, the threads blocking when all other threads are just about to free that critical section there. So that's the case we were discussing just before, right? Yeah. You probably could get smarter and say, okay, this is the case for atomics, right? You have the very fast cast loop there, but it turns out that on the sufficiently large machine it doesn't work because you now have the contention on that particular memory location when you're trying to cast over and over again. Yeah, so now you try to do the smart things like say, okay, I will do the thread local counting, and so there is no contention whatsoever. But the problems there start to unravel when you start to collapse all this thing, because you have to know all these thread local states and also handle what if thread dies suddenly and you don't account those counts there, etc., etc. So it gets really messy. So
you're avoiding the contention by basically having each thread collect its own data and then trying to combine it at the end.
Right. Yeah. So the cleaner solution is something like this. I might have the array of atomic integers. I can select one atomic integer at random and increment that. If I have enough atomic integers in my array, I could probably dodge the contention, even if I have lots of threads. And actually, this guy there is better known as the long adder in GSR 166E. It would be part of the Java 8, and it's actually performing really, really good. It performs as good as the uncontended atomic integer increment, even under the contention.
So this is using a striping technique then?
This is striping.
Yeah.
And this is the general technique. You can use that in other cases. This is just the hallmark example of that. If you can spare the communication at all, you should probably do that, because the larger machines, the machines will become larger and larger, and the performance penalty of having the shared state would be more and more, so you will probably want to provision that from the start. So you can enforce the immutability or start to use thread local states. So one of the hallmark examples for that is thread local random, which actually maintains the state of PRNG local to each thread, which again scales very nicely under contention.
Yeah, and if you look at like SciMark benchmarks, you notice that the bottleneck in it is actually
is the
random number generator from the CAS. Yeah.
Right.
Yeah, absolutely.
So false sharing. Who knows what false sharing is? Let me just start. Oh, you guys.
Yeah.
Okay.
So those guys know for sure.
Right. So false sharing. You might think that even though our memory is addressable by byte, so I can actually ask what is that byte's value there. The communication quanta in my memory hierarchy is not actually bytes. Those are complete cache lines. And the cache lines are really huge. They are like 3228 bytes long, not bits.
Yeah, commonly 64. Yeah.
On x86-64, ARMs have 32, powers have larger cache lines there. So it really helps the memory transfers, because if you are reading the memory sequentially, you are pre-reading all these cache lines in bulk. And this is really helpful for the performance of memory subsystems. But imagine you have, and this is not to scale the cache line, and you have two fields lying on this cache line. And those are not really shared. Imagine that CPU 1 is updating the field A and CPU B updating the field B. what would happen is that if the CPU wants to write to a particular memory location, it has to assume the ownership of the cache line that holds that value. That means if the CPUs are writing into this location, they will ping-pong that cache line through the memory hierarchy, especially effectively getting lots of memory bandwidth consumed just for this ping-pong.
Yeah.
And these fields could be seemingly unrelated. These fields could actually be the fields of different objects, because the object header is very, very small, and the consecutive objects could actually lie on the same cache line. So this is like something that it could hit you in the face when you're dealing with a heavily concurrent code. We know how to diagnose that. This is the hardware counters again. We will not do that at this demo. The concurrency guys know how to deal with it. You effectively pad your object instance to consume the whole cache line, so nothing else is on that cache line.
Right.
And there's the discussions in the hotspot land and the J9 land, how to actually support that from the JVM perspective.
So the thing you have to consider when you're padding is that the class loader will rearrange the variables in the way that they're ordered and everything, for one thing, and the JIT may actually dead value eliminate your padding. And so
Hotspot doesn't.
Sorry?
Hotspot doesn't. Yeah. Yeah.
Well,
you can bet.
I'm not going to bet with you on that one. But 7 is, they're doing some dead value elimination. No. Not on.
I don't think so. We can check it. Right.
We can check that. Okay.
Right, but yeah, it's the safe route is never assume that.
There's also another issue that comes out of this, not only false sharing but false synchronization. So if you put, if you mark A as being volatile, and when you flush the cache, line or drain the cache line because of that, B will be automatically or magically synchronized. If you go and rearrange your code so the code gets rearranged in the cache line differently, so that B effectively gets evicted from this particular cache line into another one, then its false protection actually goes away. And that's also another interesting source of concurrency bugs.
Yeah. So this is something lurking there in the shadows. If you're not concerning yourselves with it, that's fine. You will concern yourselves with it someday. Trust me on that. Right. Allocation profiles. So now we are down to, we actually solve the concurrency issues, IO weight issues, all this stuff around. Our test is actually running decently fine, right? So we need to figure out whether we can push harder, right? Do you want to do this?
No, I'll let you operate the keyboard. It's a nice Russian keyboard, right?
Right,
So,
right,
keyboard, right?
right,
So,
right.
yeah, okay.
Right, so it actually, that's the run, right? We don't have any errors. We are slightly above our target there, right? So we're probably not pushing for the another requirement, but still trying to meet this one.
Okay. So in this case, we actually, if we're looking at allocation profiling, one of the things we'd want to do to make sure that we're going down the right path first is actually look at the garbage collection log.
Yeah, right.
Did you collect one of those?
Yeah, sure.
Awesome. Okay.
Let's see now. I think it's here. It's the GC log, and the time is right.
Okay, so now so what we're going to do is we'll start Sensum. It's our garbage collection analysis tool.
Okay, where's it?
Got it? It's in the jar. Okay.
So you know this tool. Go ahead.
I know this tool. Okay, let's see if we can figure out your, okay. So in this case here, what we're actually going to do is we're going to load the garbage collection file up into our GC log analysis tool. Hopefully everything works. This is still alpha, right? Hopefully it'll be going beta sometime this week. And as you can see, there's a whole bunch of different things going on in this particular tool, which I won't demonstrate too deeply, but we have some sort of analytics that are basically trying to indicate some commonly found problems that we have, some heuristics to determine if you're suffering from different problems. The more traditional views here, the views that we're actually interested in looking at are all these particular graphs here. And you can see this one here is like a heap utilization after garbage collection. And actually, in this case, you can see the JVM is actually, the black line is being like...
Yeah, we can show the legend there because it's cut.
Yeah, I was just going to lift that up and see if you can, the legend, because it seems to be cutting off, right? So that's actually heap size, and you can actually see the VM actually adapting the heap size to the various conditions. Now, really what I would look at is, for this particular case here, is what we call object allocation rates. And in this case, we're at 75 million K, which is over a period of about 200 seconds. So if you do the maths on this, you can see that we're probably running, it's like 75 gigs, about 7.5 megs or gigs per second.
You ask me? You have the laptop.
Okay. Well, just checking my math or whatever like that, or divided by 2, so 3.5, right?
Right.
So this is a case where we can say that
so what's the allocation
we're
rate
probably, well, sorry?
So what's the allocation rate?
About 3.5 gigs per second.
Yeah.
So this is a case where we're probably pushing up against the capability of the CPU to write memory, write this data from the CPU out to memory. So we'd like to make this application actually more memory efficient in this particular case. There's also some other things that we might want to look at. In this case, we'll look at the tenuring summary. And we see we have another really nasty condition here. We can see that we have a premature promotion rate of exactly 100%. So if you remember the graph that we saw early this morning where we had data going from Eden into the survivor spaces, the purpose of those survivor spaces is to actually keep data in a space where it's very, very cheap to collect it. By the time we get the data into tenured space, it becomes very, very expensive to collect. So we definitely want the data to reach tenured space if it's going to be around for a long time, but we don't want it to get there if it's not going to be around for a long time, because that's just going to put pressure on tenured space, and that's going to cause more frequent full GCs, right? So in this case, what we're saying is that we're flooding the survivor space 100% of the time, which means that we have to prematurely eject data from the survivor space into tenured. And that's also obviously not a good situation. It generally means that our survivor spaces are too small for this condition. And there's some other views that we can actually look at. In terms of tenuring thresholds, we can see that tenuring thresholds over time, are really nicely densely packed around once. So it really means that that our survivor spaces are probably grossly undersized. Mm-hmm. Now, unfortunately, the garbage collection logs, the parallel collector doesn't give us the data that we need to actually figure out how much bigger we need these things to be. So we have to do a bit of guessing. But in this particular case, I'd probably say that heap size is big enough. Mm-hmm. We just need to make the young generational space bigger, and we'll make the young generational space bigger, and we'll also make the survivor spaces bigger. Now, the reason why we want to go in that route is because we need to be aware of GC frequencies, right? And so if our GC frequency seems to be reasonable, in other words, it's not causing us any lock contention issues or any other issues like that, then we probably don't want to mess with that, which means assuming equal rates of object creation from your application, what we want to do is we want to try to keep Eden the same size. So we'll trigger GCs at the same frequency. And if we make our survivor spaces bigger, that means that we need to steal memory from someplace. We don't want to steal it from Eden. That'll increase the frequency of GC. So we'll steal it from tenured.
I have a question for you.
Yes.
So why don't we just go ahead for the application and try to reduce its allocation rate instead of messing with GC?
That's, in this case, probably a better route to take.
Why?
Because the high allocation rate is not going to be solved by the memory pool sizing.
Right. So allocating 4 gigabytes per second is probably pushing the memory bandwidth boundary.
For this particular machine.
Yeah,
so you have to go back to your manufacturer to understand what the rates are that are sustainable on your piece of hardware.
So I'm quitting this.
Okay.
Let's try to do the memory profiling then, right?
Okay.
So we have our JIT right there. So we will try to do...
Okay, so in this case, we don't need to communicate with the garbage collector, so we'll just look for object allocations, and we'll record the allocation stack trace. And we'll take some pressure off here. We're not going to record everything. We're going to record every 100th object allocation. That should probably give us enough memory.
Right. So
it
had instrumented, right? So
yep.
I will restart the JMeter just for the sake of completeness here, and I'm trying to run the test again. So do you want to do that on the same load, or probably?
Yeah, leave it at the same rate.
All right.
So we can see what's going on. We'll probably just shut this off before we snapshot, right?
Okay.
So let's go and look at what Visual VM is telling us. And you want to close off the configuration thing? Okay. If you drag it a little bit over to the right, you can actually see, okay, there you go. See that little box in the upper corner over there? You click on that, we can actually get more information or take away information as need be. Normally what I do is get rid of filters. Filters are really good for filtering out the bottleneck or the thing that you want to be looking at. Okay. So it looks like we have a lot of byte arrays happening here. And so...
Do you want me to do a snapshot now?
Well, I would say let's turn off JMeter.
Okay.
Yeah, that's a good way to turn it off. Okay.
It's the obvious one.
Yeah, I like it. And let's do a snapshot now. Okay, and now let's look at the right click on that, and we're going to see allocation stack traces, right? In this case, we look for big red, because big and red is bad. We open up.
Yeah, and this is
there we go.
Yeah, this is our application code.
Now we're into our application code, and that's our causal execution path, right?
So it's stock history, right? And we probably should take the dominator, which is construct results table.
Right. Now, you know, so this is a conversation that we had prior to setting up this demo, was, you know, can we do the same thing with an execution profiler? And the argument is absolutely, yes, you can get to the same place with an execution profiler because obviously creating all of these objects requires, you know, that you execute code to do that. But I find it, especially in larger applications, or applications that are much larger than this tiny demo, that the allocation profiling often gives me a slightly different picture or a better picture than what the execution profiling does.
So this is our guy, and we know that in the stack trace we have actually the write and then get bytes. So these are all these write calls, and the method which does this is, you can see it here. Can you see the problem? Except for I'm not using the char set. We're actually generating a lot of garbage here of doing this very small strings over there, getting the bytes out of them, and trying to write them back to the stream. So we actually have our dominator is byte array. It's the same byte array that we got from that stream. So probably the thing to fix there is actually saying something like this. Say, I want string builder. This is the obvious optimization, but you shouldn't really commit to that until you prove it's actually needed. Oh, no.
Yeah, I mean, the other thing you could do is you could put wrap the output stream in a buffer.
Oh, come on.
What?
I'm puzzled how to fix it. All right, so I do this. I then do replace it with SB append. That will probably do it.
Yeah, I think that'll do it. Lovely.
No.
There you go.
And this guy should be also SB append. And for the sake of completeness, we actually unfold this guy to appends. And now we have to write it back. So what we do is say, write it as B to string.
Yeah, there's still one in the middle up there. This dot right.
Really?
Yeah.
Where?
Right there. This dot right.
Oh, yes.
Yeah, it's okay.
I wonder what would happen if I actually run.
Yeah, I know. I'm not sure
Right.
I'm not sure that we want to find out.
That's it, right? So we can.
Thanks for that. Who said that? Yeah, right.
No.
Beer for you, right?
All right. So now we can run it again. We could actually attach the memory profiler and see that the bytes are gone. But instead, we would probably observe the better throughput because we significantly cut off the memory allocation there. So you see that the average time before was how many? 110, right?
Yeah, somewhere around there.
Yeah, so and now we are having like 44, 46 milliseconds per request. So it's like 2x improvement there.
Yeah. And, you know, there's probably a bit more that could be done there. But
yeah. So this is the allocation profiling stuff. This is the allocation profiling stuff. So we probably need to talk about the JVM level. GGC is not the only contender in the JVM that you're fighting with. Other contenders are class loading and JIT compiler. So the rule of thumb is if you suspect the problem with the JVM, it is probably the good moment that you think about upgrading your JVM, because probably your issue is already fixed in the next build. Sucks to be you if you are running on the Java 1.5 or Java 1.4.2. So please consider updating your JVM frequently, because lots of performance and stability fixes are there. For GC, usual stuff applies. Kirk can talk about this for hours and hours and hours, how to tune the GC, and I understand how Kirk feels about it. So we wouldn't do that here. Please reference to other talks for the tuning of these guys. We wouldn't really tell about JITs, except for saying that you have to probably check that you are running with the particular compiling profile or profiling mode that we have, that you have to have clear understanding what server and client compiler is. Client compiler is oriented for the faster startup times, but not so optimal code. The server profiler is vice versa. It starts up slower, but generates more optimal code. We try to marry these compilers with the tiered compilation by first compiling with the client compiler and then recompiling the hot code with the server compiler. And it admittedly works, not in the all the configurations, so you have to test and report bugs in it.
it's still has some maturity.
Yeah, it is. Has, yeah, it is a very new feature.
There's also another thing I think that's important to mention here. There is another hidden, not well-known memory pool that the JIT compiler uses. Do you want to talk about that?
No.
Oh, okay.
I don't want to talk.
I
don't like to talk about it.
It's called the code cache. And if the code cache, it's a space that works different than the general Java heap spaces, but it has the same type of ideas. But that's just where we're going to put native code. If you fill that up, all this wonderful JIT technology that Aleksey's built gets turned off.
Bailout.
Gone,
yeah.
right? And all of a sudden, instead of running native code, you're running bytecode interpret mode all the time.
Mm-hmm.
So I do have a memory pool viewer that actually gives you good exposure to what that thing looks like. Unfortunately, it's not well instrumented in the sense that in a production system you can't really get to see what's in there very easily.
Yeah. If you are the compiler expert or the hotspot expert, you might probably want to fine-tune the JIT. All these beautiful hotspot command line option listings have, half of that is GC, half of what is CMS GC tuning.
Right. Yeah.
And the other half is the all sorts of compilation flags that you might find useful if you know what you are shooting for. But you have to be the compiler expert to do that. Or you can go for OpenGDK and ask advice on some particular optimization that you
I think the most common thing that people touch is decay. And that's a behavior I'm not sure that we really want to talk about here, but it's just how Hotspot maintains the counters that it uses to determine when a piece of code should be scheduled to be compiled.
We shouldn't probably talking about that, because if you're facing that problem, that's probably a bug.
No, it's low latency also.
Oh yes, it's low latency. So yeah, so in the hotspot there is the option which says what is the threshold for the performance counters in my code, overflowing which I would start compiling that method. We actually gathered the two types of counters. First one is the method entry counters, and the second one is the back branch counters. The back branch is the
it's back on the for loop.
Yeah, it's the back on the loop or something like that.
Yeah.
So you can actually tune up the threshold for going there. If you are concerned with the very fast startup and decent performance afterwards, or the low latency. But this is like the magical stuff there. I don't want to talk about it anymore. Right. So class loading, it's also the concern for the startup, especially if you are having large applications. It's not as bad as it was 5 years ago, but it still has some room for improvement. If you are struggling with the class load times and the startup times, you probably can do all sorts of tweaks there, like using the class data sharing, which is starting from a recent build of GDK is actually supported for all of the GCs, has the nice effect of the eliminating perm-gen.
Yeah.
You can turn off the verification of bytecode. You can recompile your code to get some of the new features of Java-C, like split bytecode verifier. You can increase the size of the system dictionary, which is really odd, but this is sometimes viable optimization. But you have to exercise caution in that. Because
what is the system dictionary?
Oh, this is the system dictionary. This is the native hash map which maintains the unique strings or something like that.
Right.
So and its default size,
yeah,
and its default size is really small. It's like 1,000 something elements. So you have a lot of collisions if you are beefing it up with the values. So one of the optimizations is setting it larger. If you have lots of...
So you get fewer collision rates and then less walks on collision resolution then.
Right. So we did a little demo on the allocation profiling. Now I want to show you the... we fixed the allocation problem. Sorry, we are in time. Right, so we fixed that allocation problem already. So what's next there? We go for the application stuff. For the application stuff, we have several major categories there. First one is algorithmic complexity, caching in the application, busy waiting and batching and work scheduling there. When you deal with that kind of code all of your life, you will start to notice these cargo cools going over and over. So most of the performance bugs that I frequently see in the user code is just a plain copy-paste without thinking. Yeah. So like using the bubble sorts for sorting when you don't have to have stable sorting or something like that, just because you see this nice Wikipedia article at which you have this bubble sort and it looks easy enough to implement in your code. Right. So algorithmic complexity, you should probably prefer the low O code instead of high O code, but you have to be really careful about this, because even in computer science, everyone would tell you that the O notation is actually chewing up on the constants. So it may turn out that on the lower problem sizes, your high O code is actually faster than your low O code. So for instance, bubble sorting a really small array is actually faster than quick sorting it. Not only because it has the better cache locality stuff and whatnot, but also if you count the operations that you do there, it's actually a lower operation count for the bubble sort. So you have to figure this out on your own as well.
Yeah, instruction counts still count.
Yeah, instruction counts still count, right. Caching. It looks like the solution to just about any performance problem in the wild. So if you have troubles with something, just cache it. It's not particularly the solution in some of the cases, because caching blows up your memory footprint. It gets more work for GCs and whatnot. So you have to be careful there as well.
Yeah.
You cannot just blindly cache everything that you have in your application, because otherwise you are heading for the trouble.
There's a life cycle cost to caching, right? So, and it's really because of garbage collectors. Garbage collectors are run to failure. Failure means I haven't been able to collect, right? So the most expensive path is dealing with live objects. So if you cache, you're going to be cranking up the number of live objects that your collector has to deal with on an ongoing basis. That means, so sometimes it's just cheaper to either stash the object or recreate the object than it is to keep it in memory.
Yeah, so I have this frequent question of whether you should pool your objects, and the answer to that actually depends on what is the life cycle of your object
right.
there.
So
Pooling the sockets is fine. Pooling the simple object is not fine at all.
Yeah, it depends on the cost of getting them. And
Yeah.
for low latency guys, then what they'll do is they'll allocate
In advance,
primitive buffers and just fill those. But then in those applications, the garbage collector never runs.
Right. So other thing is busy waits. I frequently see that the smart guys who are not latency oriented, but just the smart guys which say that blocking synchronization is bad, and I will just wait for some condition there, and then you burn the cycles sitting there. And the bad part about this kind of problem is that it pops out in your production environment, and you don't really see that on your development environment because your machine is probably, or system is probably smaller. So your natural instinct, if you're not oriented for very low latency, is blocking. If you're latency oriented, you should be 100% sure that the busy wait is actually profitable and not burning the cycles. Right. So execution profile. Let's go back to this application. So now we had executed all of the requests, and now we are down to 42 microseconds per request, which is already very good. But we want to push forward with this, right?
Milliseconds?
Milliseconds.
You used to optimizing JIT, right?
Right, so I will restart everything again and again and again. Why it's doing the exceptions? It never did the exceptions before.
Well, that actual Sun Sax parser isn't actually thread safe. So I lied when I said you could take the synchronization off of it. Oops. But it works most of the time, yeah.
All right.
Well, if it throws an exception, just try again. It's cheaper.
You know that your market price is now getting lower? All right, so I started. Let's load it with some work. So it's loaded, and I will do the sampling profiling. I will probably profile everything.
I'm still deciding if I should object to that, you know. If it throws an exception every once in a while and you can just rerun it, and it's overall cheaper, I'll go for the exception.
Yeah, right. Until you're stuck with the code which spurs out the exceptions every nanosecond. And you start to think,
that's a different
what
case.
Moron had actually conceived that?
Exactly.
All right, I'll let it run for a while. I can probably make a snapshot at this point. I will pick up one of my worker threads. Let's see. Oh no, not this. Oh yes, this guy. And I will go through the call stack and find my usual dominator. So this is just the read. So I'm not interested in that. And I'm going down and down and down. Let me see what I have there.
So in terms of this profile, are we actually looking at wall clock time measurements here? Or
no, it's the sampling profiler.
At CPU time.
No, it's not a CPU time. It's not
wall clock time. Yeah.
Yeah, it's wall clock.
Okay.
All right. So we see that the hottest method is, what do you know? Again, closing price, blah 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 load, and what is doing there is parsing XML. So let's take a little brief look into that method again.
That's a really bad method. It's the third time it's shown up.
Yep.
Who wrote that?
I know the guy. All right. So this is the who is actually doing the load. So it does this parse XML code right there, and this is our major contender. So our instinct would be probably to cache these XML results, not rereading from the disk and not reparsing it all the time. And by the way, I see these lines over there, which is somebody is trying to do that caching done already, but it's not working. I could dive in and say, okay, I see this field cache enabled, and it's initialized here. And by the way, this is the property that I need to tune, right? Let's see if I can find it. I think it's in the properties there.
Try that one. That should
Oh,
work.
yeah.
And where is it? Oh, it's set false. Ah,
See how performance engineering is easy, right?
missed that one. Darn, you're good.
Just, yeah. So let's start it again. Come on. JMeter, start. Aggregate report.
Ha ha ha, 100 milliseconds. Oops,
Just wait for it.
oops, oops, yeah.
So it was
29,
40 microseconds before, right?
29, 20. Yeah, we have to wait till the cache warms up, right?
Mm-hmm.
So this might be a case for preheating caches.
Probably, yeah.
13,
but
12?
it's stabilized, right? 13. There.
Look at that. Oh, and it's got a minimum of 1, too. 11.
We can actually try to go forward and do the MP stat stuff there. So now, even though we solved all these concurrency problems there, we actually do the work so efficiently, so we have lots of idle time. So we're just consuming that little bit of my CPU there. So we are paying less for our cloud subscription now.
Well, that's performance tuning, right? You make everything completely dependent upon the CPU and then remove the dependency.
See that? 8.
Perfect. 8. Brilliant. Lovely. Congratulations.
Yep. Where's my invoice?
Fantastic. Okay.
Right.
We're done with this one then, right? Okay.
Right.
We're done with this one then, right?
Right. So the remaining part that I want to talk briefly is that this is where most of the applications stop, and this is where most of the performance engineers which are going for the customer sites stop. And we are, as the library developers, are actually going even deeper, and the hardware guys are going even deeper. We are going for the CPUs. So after you fix all these problems with the applications of whatnot, systems, whatnot, you are dealing with the plain CPUs. And the important thing that I need you to digest is that our world is now dominated by many CPU machines, many core machines. And that implies that on average system, you have plenty of CPU. So you have enormous amount of computing power, which means that CPUs are the least depleted resource, usually. Yeah. It's really hard in current world, with the current application and the current hardware, to actually saturate CPUs up to the level they are actually start to be the capacity problem. But sometimes you do. So there are 3 distinct cases there. One is you have not enough CPU frequency, and you deal with that with the overclocking or even setting the CPU frequency governors. This is the single exception from that CPU rule. Actually, the CPU governors affect the performance of the memory subsystem. So setting up the CPU governor is probably beneficial for your general application performance. You have no idea how many servers are running with the on-demand performance CPU frac performance governor, which kind of cuts out the latency and throughput benefits, but brings in less power. So if you're up for the performance, watch for that guy.
But that does come at a huge power cost.
Yes, it does. Yeah. So you need to balance again. You might run out the execution units, and at that point you probably should be going for the specialized code, probably going for the either native code or actually writing JIT intrinsics, which is the hardcore but still bearable. Or you can go for the specialized hardware, and probably the hardware that gets the support from the JVMs or some sort of libraries. Or you just hop in more CPUs there, which is the solution to most of the problems.
So one of the things you have listed up there is the GPU, and actually with Project Sumatra, we should have access to the GPUs as part of the standard JDK.
There's some anecdotal example of, I actually ran out to the execution units once. There was the case when we were doing a very CPU intensive, floating point intensive operations. So we were running on the very heavily threaded platform. And it turns out that platform was running out of the CPU execution units. So if you're running the integer test, it scales really, really good up to the place you have the CPU count there. But if you're trying to do that for the floating point, you are actually saturating the system much earlier because you run out of the functional units. So the solution there could be, breaking up this homogeneous work of just computing the CPU and interleaving that with the other kind of work. But this is hardcore, and you probably wouldn't get there. So just know it could happen, but don't count for that. All right, ILP, processors speculate aggressively. So even though your instruction stream is sequential, you have lots of parallelism inside that stream, and the CPUs are benefiting from that a lot. So it may turn out that the ILP in your code, instruction level parallelism that is not that great, so the processors could not speculate aggressively, and at that point you probably want to help them out. So one of the hallmark examples is less branches, which you can even control on the Java level of not actually issuing the branches. Or you can ask JIT compiler for the optimizations or the new optimizations which do this automatic if conversions to the more branchless code. So we do that routinely in the compiler.
So this is a technique that we've used routinely also, especially on highly pipelined architecture, is we actually break things up into 2 for loops. So one for loop would just go and do the calculation very quickly, and the next for loop would actually would pick out the actual results that you want. So you'd actually end up calculating more things than you needed, but that was actually faster than just selectively calculating what you wanted with a branch.
All right. Closing thoughts. Probably I should first look at the demo. So it's 7 microseconds.
That's pretty good.
Yeah, and it was 25 seconds before.
Yeah.
Or
longer, actually, it was in the minutes.
Yeah, orders of magnitude
really
performance boost. Yeah.
So
our closing thought is this.
Yeah.
This is actually the same mind map that we were walking through. It's actually convenient to aggregate what you think about performance and walk through this as the decision tree in order to untangle particular performance problem. So it's there in full format, vector format in the slides. You might want to download it and use it.
Yeah.
I think use it.
Yeah.
I think
we have 10 minutes left for questions, so we're open for questions. If you have any issues.
Did we miss anything?
Well, we missed quite a bit, actually, but
you know that. They don't know that.
They don't know that. Sorry. Yeah. Did we miss anything? The role of the database.
Oh.
Yeah, this is sort of more my territory than than what he does. The role of the database. The role of the database is to slow your application down.
And store the data meanwhile.
Well, he can't say that because he actually works for a database company, even though he doesn't know anything about them. And store the data into nice formats. I really don't know what to say about databases except for you just have to be really careful about how you use them. Generally, the solution to a lot of the problems are caching. And to plug an Oracle product, I would say like Coherence has been an excellent solution for dealing with a lot of database problems. JPA has been a nice solution, but you have to be careful because some of the implementations will do very unobvious things. For instance, it's not uncommon for us to see 10, 20,000 SQL instructions being issued for some requests that you think should only take like maybe 2 or 3 or things like that, right? So you get some strange ways of getting joins done where they should be actually done in the database. So, it's wonderful technology. It served us very, very well. And so I think there's still a lot of life in it. I think the NoSQL stuff is also extremely interesting in terms of what it offers. But
I actually have the slide for that. Can I do that?
Yeah, go ahead. Put it up. That's fine. Which one is that? That's the...
Yeah. So we frequently hear that complaint of, well, lots of complaints about, I think our database is actually slowpoke and we need to migrate to this fancy buzzword. And you frequently hear,
to buzzword,
in the buzzword, you frequently hear NoSQL.
Right.
Which might be the answer, but before you actually do this kind of performance analysis stuff and actually figure out that the database is the problem, it's premature to go from the well understood or well fitted solution to something that greatly breaks your application or incurs the development costs that you have to account.
And quite often you're trading one set of problems for another set of problems in this case, right? You know, like the Cassandra guys are off writing slab allocators, which is like a really scary place to go because you're moving problems where we have excellent tools to find and diagnose them in, right? We're moving those problems into spaces where the tooling is much less well-defined, not nearly as good, and they will run into problems. So, you know, I have a lot of respect for the people who write the hotspot garbage collectors. So if you're thinking of writing a slab allocator to try to solve some of your memory issues, you know, or using one, you have to be aware that when you get to a certain level of granularity, you're writing your own garbage collector. And these guys that are writing garbage collectors are quite brilliant. And, you know, I personally can't imagine myself writing a garbage collector.
Yeah, Tony had this headline of collecting garbage for 15 years.
Right. Yeah, Tony Prentice. Yeah, exactly. And yeah, so make sure you're not trading one problem for another. Again, make sure you got the right measurements to see what's going on. Quite often what we find is that people don't even realize that their database is being overworked with the 20,000 instructions. So what we often do is we'll probe in at that level and say, look at this. In one application we had, where there was a single button on a browser was giving you 132,000 queries to the database. Nobody knew. Because when you get into these large, complex, enterprise-wide applications, it's very difficult, it's very easy to miss these things, you know. In another application, we just had one, like you know, this was what we got right from time budgeting, right? They said, oh, the application is slow because of the database, right? It turned out to be an NTP server stuffing up the out channel on the network stack, right? So it wasn't the database at all. And that was the difference between being able to get through like 900,000 transactions an hour to our target was like 1.5 million transactions per hour. So, you know, just little things like that. If you don't have the right measurement, you're not going to see it, right? You know, when we pick that off from time budgeting, it's like, oh, in is good, out sucks. You know, what's going on here? Let's get a network sniffer and see what's going on. Any other questions?
Yes.
I don't see that. Sorry, there's a big light there.
We have a problem with a zipped message on a JMS queue, and when at the time that you invoke the get text message, it unzips automatically, and then it takes, when it's zipped, it's a size about 60 megabytes, and then when it gets unzipped, it takes about hundreds of megabytes on the heap.
So you have something that when you unzip it, all of a sudden takes hundreds of megabytes as opposed to, it's a JMS message you're saying? Sorry, just trying to understand it from this point of view. You're saying, sorry, can you say that, repeat that again?
We have a zipped message, which
Right.
is automatically zipped by WebLogic on the JMS queue.
Right.
And then when it's zipped, it's about 60 megabytes, and when it gets unzipped, it gets automatically unzipped when you invoke, try to get the text out of the message.
Yes.
Then it takes hundreds of megabytes. Do you
Yes.
have any idea why that would be?
Well, it's very cool compression ratio, I would say.
I would say that's a very cool compression ratio. That's just the nature of zip files. You can't really pick, I don't know, I don't know, you can't really pick pieces out of a zip file. You really have to unzip the whole thing in order to do that, unfortunately. Now, you know, if this is, I imagine you say that this is a problem because it takes a lot of heap space to do that.
It takes a lot of
So,
space, much more than...
In some cases, what I would do is I would try to get that work done in a disposable VM. right? So I might just wind up a VM just to do that particular piece of work. And then when I'm done, I'll just configure it so it can manage that piece of work. And then when I'm done, I'll just dispose of the VM.
Can you actually turn off the compression and see what penalty you will have for the bandwidth that you actually consume there?
Yeah, the other side doesn't get the message on the queue anymore. So
Yeah, it's so big that it actually wouldn't even get through. That's a pretty huge message. Yeah, the only other thing you can do is figure out how you can chunk it.
Yep.
You know, I think, you know, chunking might be a better answer in that case also. Anything else? Oh, we have one over here.
Yes.
You have to shout it out so we can repeat it so everybody can hear.
Increasing the number of threads to overcome performance problems. But I'm missing the point of event-driven event loops.
Event-driven event loops.
Event loops, you know, like we have in OTM and Scala, and also using it now to
Yeah. Yeah, so
it is generally true for event-driven frameworks that you don't have to have more threads. For our particular example, we were using blocking threads. So at that point, we have to make for the deficit of the blocking threads with the higher thread count.
right.
So this is the actually the hallmark distinction between event-driven and the non-event-driven frameworks, that you don't have to have that much of the threads. So you're right. If you are having the event-driven framework, you don't have to beef up the threads. If your threads are utilized and you know there is no problems with this threads blocking somewhere, that's okay.
But I would say that there's a cost to this event-driven framework, which means you at some point have to transfer data, and that transfer is not free, right? As you can see by the slide that had all of those levels of memory protection, like concurrency and stuff like that. So in this case, you know, like I've actually benched the ACA framework that's written in Scala and stuff like that, and it does incredibly well, but it's still not a free handoff, right? And in many cases, what people have done, especially in low latency worlds, is they said, let's avoid the handoff altogether and just do everything single-threaded, right? And they get much better performance in a single-threaded world where they don't actually have to hand off to another thread. And we've actually seen this effect in virtualization, where if you take a VM and tie it to a single core on a CPU, so you can fast path it to memory, then you'll see in this case, if we can divide the work up, between VMs, then that we can actually get better performance than if we actually thread this thing, because the handoff costs start dominating the workflow.
I think our time's up.
Is it?
Yes.
Well, we can take another question if there's there, but if not, we'll release the crowd to the evening.
Right. Thanks.
Thank you very much for attending. All right.